All right. So as people come in, we'll move along. Last time we did start the partial fraction stuff, and essentially, well, you were here, but others, the start of it was like this. We know how to integrate 1 over u to the n, and just u to the any power. On those last two, that's as long as the n is not 1. If it's 1 over u to the n, then we revert back to natural log from the first version. And then the polynomial u to the n, we know how to integrate that. And we know how to integrate that anytime that the u is linear. So anytime that the u is linear, it's done in the same way. This one is integrated as natural log of u, and then you have to divide by the coefficient of the linear piece. And then this one, u to the n plus 1, divide by n plus 1, and then again, divide by the coefficient of the linear piece. This, you change it to a negative n, and do the same thing as we did here. So we always have those. And so our goal is to take a messy looking rational function and make it look like combinations of those. All right. Sorry. Yeah, we'll do it that way. So eventually it's going to require factoring a denominator and then breaking that big fraction into as many small pieces as possible. Okay. And when we figure out the denominators to use, then we have to find the individual numerators. Now, in the last class, we did this one where we already had just a linear denominator, okay? And we saw that if ever we have a rational function whose power is higher in the numerator than in the denominator, so a polynomial with higher power in the numerator, then we'll go ahead and divide that and break it into a couple of pieces. And then we'll have some remainder over the denominator. Like in this case, we had a remainder over x plus 4. And so if the power in the numerator is higher, then we divide until I get a power in the numerator that's smaller. So that's what we're going to focus on in the next few examples. All right. We're going to take and integrate these. And we're going to focus on what happens when the power of the polynomial, or if the degree of the polynomial in the numerator is smaller than the degree in the denominator. So denominator has larger degree. Now, this is going to require factoring the denominator. And then my goal is going to be to break that ugly looking rational function into multiple easier to deal with pieces. Through that factoring process. So let's go ahead and factor the denominator right now. Factors of 6 that add to 5 are 2 and 3. So that means since I have a 1 out front, I can do this, I can just factor the 6. It's gonna be x plus 2 multiplied times x plus 3. Now, what that does is that shows me how this integration is going to be rewritten. Since I have the denominator that's x plus 2 times x plus 3, what that means is I can create 2 new fractions that are going to add up to this fraction. In particular, what I'm going to do is I'm going to create a fraction with x plus 2 as its denominator, and then a fraction with x plus 3 as its denominator. Now, the key thing is, what are the numerators going to be? And as of right now, I don't know. So we're just going to leave those as general A and B. Now, what we're saying is that these 2 fractions should add up to this one. And if you think about how fraction addition works, if I say A over x plus 2, I'm going to leave some space, plus B over x plus 3, again, I'll leave some space, add up to do this. Well, if I were to add the left-hand side, what I would need is a common denominator. So I would take the A and on top and bottom, multiply by x plus 3. The fraction with the B on top and bottom, I multiply by x plus 2. And now my denominators are all set. And we get the following equation. A times x plus 3 plus B times x plus 2. Since these all have the same denominators now, the numerators have to add up to x plus 1. Once you get used to that, once you've seen that a couple of times, you'll probably skip writing this step and just go right straight to the numerator step. Now, let me distribute AX plus 3A plus BX plus 2B is equal to X plus 1. Normally I keep writing, but I'm running out of room, so I'm gonna go up. Now, this is one equation, but it's actually 2 equations in some sense. Because there are the x terms which have to be combined, and then our constant terms which have to be combined. All right. So because of like terms, what we have is that when you combine AX plus BX, you have to get X, or just 1x, right? The AX plus BX are like terms. The constant terms are going to be 3A and 2B. Those have to add up to the constant term on the right-hand side. And so essentially what I have is a system of linear equations. The two linear equations are that A plus B has to be 1. That's just the coefficients have to add up and give me 1. And then 3A plus 2B has to be 1. And this is a system of linear equations with two variables, so I can solve that. There's a lot of different ways to solve. One way would be to multiply the top equation by -2. And then combine the equations. When I combine the equations, I get 1A, no B's, equal to -1. And if A is -1, I plug it back into here. And B therefore has to be 2. You could have also plugged it into here and got a B value of 2. So I simply solve that some way, shape, or form. I find the A and I find the B. But this is the general principle. Again, usually I start here. I say I want common denominators. So I kind of do the thing in this step in my head. Once I have an equation, now I split it up into different equations with like terms. And usually what I'll do is kind of skip this version and go straight to that version. And I find my A and B in this case. So A is -1. And B is 2. Now, each of these fractions is a really nice integration because it's just a constant number divided by a linear piece. And we know how to integrate constant divided by a linear piece. That is going to be -1 times the natural log of x plus 2. The coefficient of the x is 1, so dividing by 1 isn't going to change anything. And that second one is going to be 2 times the natural log of x plus 3. Again, coefficient of x is 1, so dividing by 1 doesn't change anything. And then we end up with a plus c at the end. And that's my final answer. So the integration piece is pretty straightforward. And that's what partial fractions is all about. It's rewriting a rational function into smaller pieces that are easy to integrate. The hardest part is finding the A and the B through this process. So I factor the denominator, I figure out what the fractions are gonna look like. I use getting common denominators to figure out what my A and B have to be. And then I have to also be able to solve a system of equations in A and B. By the way, do you know this? Have you guys ever dealt with matrices and solving this through matrices? Okay. The coefficient matrix or the augment, let's do the augmented matrix. The augmented matrix of this would be 1, 1, 1, 3, 2, 1. Sometimes people draw a vertical bar right here to show where the equal signs are. But this system has this augmented matrix. Again, some people will draw a vertical bar just so you see where the equal sign is. I don't necessarily do that. And if we just ask our calculator to put that in row reduced echelon form, it'll actually do all of this work for us and just give us an A value and a B value. Let me show you how that's done on the calculator, at least once. Okay. I'm going to try to do that on the calculator. Hopefully you can see. Here's the about. Actually, go this way on my desk. There it is. All right, so first thing, I go into the matrix menu, which is on the left-hand side of the calculator, down about 5 buttons on the TI-84. This gives me a bunch of matrices. I want to edit one of those matrices. Our matrix, our augmented matrix, had 2 rows and 3 columns. So it's 2 by 3. You tell it how big the matrix is. What are the dimensions of the matrix? And so the matrix was 1, 1, 1. And then 3, 2, 1. Does that make sense? So now matrix A is input in my calculator. I go second and then quit, back to the home screen. And then I want to put that matrix in row reduced echelon form. So I go second, back to the matrix menu. Do the math. Row reduced echelon form. Second matrix menu for matrix A. So row reduced to form of matrix A. And you get this matrix here. 1, 0, -1, 0, 1, 2. So once you use your calculator to do that, that row reduction, 1, 0, 1, 0, 1, -2. And remember, your augmented matrix was taking off coefficients. So what this says is that 1A plus 0 B's is equal to 1. That's also known as just A equals 1. This says 0 A's plus one B is equal to -2. That's also, this B is -2. So if you wanna not work quite as hard and you wanna utilize technology, then you can just row reduced echelon form a matrix in order to make your life easier, to get that A and the B. Does that make sense? All right. Let's do another example. We're gonna look at this question, 7 divided by x squared minus 8x plus 12. Integrated with respect to x values. All right. Now, the process for this one is very, very similar to the last one. Okay, there is a little bit of a thing we have to watch out for, but that's okay. So let's start by factoring the denominator. Since this x squared has a coefficient of 1, when you factor the denominator, it's going to be x plus or minus a number times x plus or minus a different number. So I need to look at factors of 12 that add up to -8. -6 and -2. And it really doesn't matter which one you put first. If you want to do the x minus 6 first and the x minus 2 second, that's fine. If you want to switch those, that's fine as well. Which brings me to my next point. When you set up your integration, I don't care which one you write first. If you write A over x minus 6 first and B over x minus 2 second, you're going to get a particular A and B. If I choose to do A over x minus 2 and B over x minus 6, our A's and B's will just be swapped. So you're going to get the same answer both ways, except like in the last one, we had A was 1 and B was -2. If we'd have flipped the denominators, then A would have been -2 and B would have been 1. Does that make sense? So it doesn't matter, you're gonna get the same result either way. Now, I'm gonna do this in my head. If I want to make this equation, this summation, equal to that, I'm gonna require common denominators. So to get common denominators on the fractions, what am I going to have to multiply by A over x minus 6? I'm going to have to multiply by x minus 2 times another x minus 2. Okay. I'm going to leave off the denominator because the denominators are all going to be the same in the end. In order to get common denominator over here, I need to multiply both the top and the bottom by x minus 6. So B is going to be multiplied by x minus 6. A is gonna be multiplied by x minus 2. And when the numerators add up, they're gonna have to equal the numerator over here. In particular, they're gonna have to equal to 7 when we add them up. So when we get common denominators, add up the numerators, that process is gonna lead us to having a 7. Now let me multiply that out. A x minus 2a plus b x minus 6b is equal to 7. That's going to give me, so this is one equation right now, but remember that equation can be split into two based on like terms. So first, the x terms, say ax plus bx have to be, well, how many x's are on the right? 0, right? So a plus b, the x terms, have coefficients that are a plus b, has to give me 0. The constants have negative 2a, negative 6b equals 7. I wrote that too small, but better read that. Okay. Again, I like to save myself time, so I just put row reduced echelon form. Usually, I'm fairly efficient with my calculator. I'll do a row reduced echelon form of the augmented matrix. Again, the matrix is 2 by 3, 2 rows, 3 columns. Now, depending on whether I want decimals or fractions, when we do this, I got, let me write it down. 1, 0, 1.75, 0, 1, negative 1.75. Is that what you guys got? And then it actually, if you just say, if you go into the math menu and say convert that to a fraction, it'll convert all the entries in the matrix to fractions. So if you'd rather deal with fractions, just use your calculator to convert that in reduced form. Those fractions are 7/4 and negative 7/4.
There's something wrong with the calculator.
Good, but,
Cause I didn't get those numbers.
okay.
It sound like error.
What's the type of error?
Wrong values or variables. Yeah.
Okay, so you're in the wrong spot to make sure you're in the matrix menu. When you put in 1, 1, 0, negative 2, negative 6, 7.
Yeah, I put it in, like I put it through the edit page.
Yep,
These two.
I can take a look at it in a second. As far as using decimals or using fractions, it's not a big deal either way. Okay, which one you use. If Moodle asks you to use fractions, use fractions. If Moodle asks you to use decimals, use decimals. I'll use fractions right now. But what this means, sorry, forgot to write that, is that A is 7/4 and B is -7/4. So all of that work right there was just to figure out what the A and the B were, right? Now, once I know the A and the B, I know that it's gonna be 7/4 over x minus 6 plus -7/4 over x minus 2. Like I was saying before, if you'd have swapped the order, then at this point, it would have been exactly the same fractions, just in different order. Okay. I can integrate this because it is just number over a linear piece. So we're gonna take that number 7/4, multiply times natural log of x minus 6. I would divide by the coefficient of x, that's a 1, so that's not gonna change anything. And then minus 7/4 times the natural log of x minus 2. Again, I would divide by the coefficient of x. If it wasn't 1, since it is 1, it's not gonna change anything. So won't write that down. And then we have a plus a constant, always at the end. Now, I'm leaving all of my answers like this. And you probably should too. Because of all of the algebraic properties of natural logs, these could be rewritten. All right. These could be rewritten into like a big single natural log, but it takes some time. So I'm gonna leave them like this in general. But if you see some other answer and it looks like, I don't know, natural log of x minus 6 over x minus 2, all raised to the 7/4 power. And that's all inside a natural log. That's another way of writing this whole thing. Okay. Or fourth root instead of 7/4, you use fourth root to the 7th power. All kinds of different ways to rewrite. Okay, yeah, natural log, if you remember, has some weird algebraic properties. That's all. Get that there. So there's a lot of different ways to rewrite these things sometimes. But that's the basics of it. Basics of partial fractions is that we want to split this into two fractions. And the two fractions are going to have denominators that are determined by the factoring versions of this. Of our original denominator. Okay. Now, so far in examples 2 and 3, our original denominator factored into two parts. That doesn't always have to be the case. Our original denominator could factor into 3 parts, like this one. Factor out an x, and you're left with x squared minus 4. X squared minus 4 factors into x plus 2 times x minus 2, right? And then you're going to end up with 3 fractions. I want you to go ahead and start this one, you might not get all the way through it, that's fine, I'll give you a couple minutes to work on this one. Let's see. Couple minutes. Now, how do you do the A?
I didn't, thinking no troops, include any.
That's what I did, second matrix. And I got that matrix. And then if you do second matrix, then row use echelon form. And say row use echelon form A, should get that.
It was different. We got, it only showed us.
So the error, I didn't say what error. Yeah. Yeah, I'm sure. Yeah. All right, let me go ahead and start this. So the denominator is a cubic polynomial. So I need to factor that cubic polynomial into as many pieces as I can. And if you factor it, it factors into three linear pieces, which are all distinct. X, x minus 2, and x plus 2. That means I'm gonna have 3 fractions. And it doesn't matter what order they're in. If I do this in this order and you change the order, then you will get the same 3 fractions that I got. Just our A's, B's, and C's will be different. And I know I'm using a C here just for that order. We'll add on a plus comment at the end that won't be the same C. Will not be the same C. So here's the trick. In order to get a common denominator, since we have 3 factors, what I need to do to this first equation, or first, let me say it this way, first fraction, the A over the X, is I would need to multiply top and bottom by both the X minus 2 and the X plus 2, the 2 left out. So the A would need to be multiplied by X minus 2 and also X plus 2. the B has x minus 2 in its denominator. So if we were to get a common denominator, we need to multiply by x and also x plus 2. Similarly, the C already has an x plus 2 in the denominator, so we need to multiply by the x and the x minus 2 on both top and bottom to get a common denominator. Once all of those are multiplied out, that whole big thing will be your numerator, and it'll all be over the common denominator. And it has to be equal to this numerator in order for this statement to be true. In order for this equality to be true, we need that whole thing to be 5x squared minus 12x minus 12. Now it's going to take a minute to multiply this out. We have a, when I multiply this out, I get x squared minus 4. B is going to be multiplied by x squared plus 2x. C is going to be multiplied by x squared minus 2x. So we're going to get a x squared minus 4a plus bx squared plus 2 times b times x plus cx squared minus 2 times c times x equals 5x squared minus 12x minus 12. Now, this is a big equation, but I can break it into 3 parts. The x squared terms, those coefficients are a plus b plus c on the left-hand side of the equation. And that will have to add to 5. So a plus b plus c has to add to 5. The x to the first terms so x to the first, we have 2b minus 2c equals negative 12. And then lastly, our constant terms. The only constant term on the left-hand side is minus 4a. And on the right-hand side, I get minus 12. So I now have 3 equations with 3 variables. This is where the advantage, the time advantage on the calculator really is beneficial. If I were to create an augmented matrix and row reduce it, the first equation would be 1, 1, 1, 5. The second equation has no a's in it, so I'd go 0 for my a spot, 2 for my b spot, -2 for my c spot, equaling -12. My constant term equation has -4, 0 b's, 0 c's, and then a -12. So when I row reduce that, by the way, this is 3 by 4, 3 rows, 4 columns. There we go. I ended up getting the following row reduced matrix, which basically says A is equal to 3, B is equal to -2, and C is equal to 4. Again, that's a lot quicker, generally speaking, than trying to solve the like terms by hand. Those like term equations by hand. Oh, I missed a row. So all of this work down here, which is the majority of the work. I know I don't have the space to write lots of things below. I'd probably write just all of this below for a while. If I was taking notes myself on paper. But all of that just is to tell me that this integration that I started with is the same as 3 over x plus -2 over x minus 2 plus 4 over x plus 2, all integrated with respect to x. Once I have that, this is a really nice, straightforward integration because there's no coefficients on any of those x's. Or I should say no coefficients. There's an implied coefficient of 1 on the x. And dividing by 1 doesn't change anything. So it's 3 times natural log of x minus 2 times natural log of x minus 2 plus 4 times natural log of x plus 2 plus some constant. Again, this c is not the same thing as that c, right? This is just my final arbitrary constant at the end. I use c as just a placeholder for some number I didn't know up there. That work? And again, I'm gonna leave it like this. This could be rewritten as one big logarithm plus c if you wanted to. If you wanted to use the rules of logs to rewrite that, it is doable. But I'm just gonna leave it like this. And if you look in the back, you're doing your homework, or if you're doing some practice problems like from the book, and your answer doesn't match theirs perfectly, might be a log rule. Why? By the way, that's also a trick that oftentimes when people are doing their homework, if they're trying to do stuff and get hints from like Wolfram Alpha, if you've ever used that website, or like a Chat GPT, a lot of the times they don't give you the answers that you would normally get through the same process we do in class. And so they may give you an answer that looks like natural log of x to the third times x plus 2 to the fourth divided by x minus 2 squared, plus c or something like that. And you're like, how did they get that? Well, their process may have been different than ours, and then it's algebraically equivalent. Which means, for the test, if you give me some answer like that, then it sends up red flags that wasn't all on the up and up, So. And the same thing happens in 6.3 as well. Section 6.3, if you ask section 6.4, 6.3, you ask some sort of a computer algorithm to solve it, sometimes they'll give you some algebraic equivalent. Like, why would anybody have done it that way? Well, no human would have done it that way, but some algorithm on a computer would have. Okay. So that's just to say, be wary of those algorithms on computers. Right? Be wary of that. You're getting strange looking answers. They're probably doing a different setup, different techniques. Computers are really good at doing real cumbersome techniques quickly, where people were really good at doing like substitution stuff. Interesting kind of tricks. Okay. So let's do the next version of partial fractions. This example will kind of show you what happens in one situation that could arise. So we want to integrate 4 minus x divided by the quantity x squared plus 6x plus 9. Integrate with respect to x. So just like always, we're going to factor the denominator. When you factor the denominator, again, I've made all these pretty easy to factor. They've had 1 as a coefficient x squared. So when you factor, you're going to look for factors of 9 that add up to 6. It turns out that's x plus 3 times another copy of x plus 3. So far, all of our factors have been unique. So what if we have a double factor? That's the whole trick here. If you would have done the A over x plus 3 and the B over another x plus 3. If you think about this, things are gonna be strange when you go to solve. Okay? So we don't wanna do this. We don't wanna write that. If you have a double factor, what you do, does that make sense why this would be strange to solve? You'd essentially get a situation in which you go like A plus B equals 4, because that's the coefficients of the x part. And then you get 3A plus 3B equals -5, because that's the coefficient, that's the constants. And when you try to cancel these, you're gonna end up with a no solution. All right? So it's gonna throw everything off. So instead of doing this, what we do is we start out, we say, well, we do have one copy of x plus 3. So I will use the A over x plus 3. And then my second fraction, what I'm gonna do is I'm gonna do B over x plus 3 squared. This is that other version. Remember, we were saying u to the n is nice to integrate. 1 over u is nice to integrate. Well, 1 over u to a power is nice to integrate. So that's what we're gonna do. So if we do have a copy, the first one is to the first power, the second one is gonna be raised to the second power. And you know what? If we had another copy of x plus 3, we'd have another fraction that would be c over x plus 3 to the third power. And then if you had 4 copies, you do plus d over x plus 3 to the fourth power. You just keep raising the powers, however many copies you have. Now, here's the weird thing. To get a common denominator in this first fraction, I need another copy of x plus 3. So I multiply top and bottom by another copy of x plus 3. This fraction already has 2 copies of x plus 3, which is exactly what we want, right? So that second fraction doesn't have to be multiplied on top and bottom by anything. Or you could say multiplied on top and bottom by 1 if you like. And when combined, they have to combine to create the numerator of this first fraction. Is that okay? So ax plus 3a plus b has to equal 4x minus 5. If you look at the x terms, we have an ax on the left and a 4x on the right. So the x terms tell me a has to be 4. The constant terms tell me that 3a plus b on the left have to be the constant terms on the right, which is -5. Now, if you want to use a matrix to do this, that's fine. Since we only have 2 variables, one's a, one's b, and I already know the a, it's gonna be pretty easy to find the b. Just plug in 4 in here, that second. So we get B is -17. Everybody okay with where I got that? Subtract 12 from each side. So there you go. A is 4, B is -17. Again, if you want to use the matrix and row reduced echelon form of the matrix, that's fine. I just thought this was quicker this time because I already had the A. A was kind of given to us. I tend to like in these situations where I have something squared in the denominator, I tend to like to rewrite that before I integrate. Just to make it easier on myself. When I have something to the first power in the denominator, I can recognize that's going to be a natural log scenario. But when I have something squared in the denominator, I tend to rewrite that and then put that something to the -2 power so that I can use my power rule. Variable to a power rule. Again, I haven't integrated anything yet. I just rewrote things. So keep the integration X. And now I can integrate. So that first thing is going to be a 4 times the natural log of x plus 3. Once again, I divide by coefficient of 1. When you raise the exponent by 1, you get x plus 3. When you raise it by 1, it goes from -2 to -1 plus 1. And then your coefficient is going to be divided by the new exponent. So it's going to be divided by a -1. And then it would also be divided by the coefficient of x, that's just 1, so that's not going to do anything. So that's just the standard exponent rule. So we get 4 times the natural log of x plus 3. If you want to leave it with a negative exponent, you can. You can write 17 times x plus 3 to the -1. That's okay. Or if you want to rewrite this as saying 17 over x plus 3 to the first power, you can rewrite it that way as well. Right? Doesn't matter. I think I'll just leave the negative exponents in there for right now. But again, you can rewrite a lot of these things. Any question about that process? So if you have repeated factors, the first one is being raised to the first power, and we do the same factor raised to the second power, and we do the same power raised to the third power. If we had 3 factors, if we had 4 factors, you'd have a 4th power. Oh, sorry. I think I'm going to skip example 6 and go straight to example 7. I want you to factor the denominator and then think about how the setup is going to look. Factor the denominator. Think about, what's it going to be? A over something, B over something. Alright, so let's, let me go ahead and do this. First thing, I'd factor out an x. And I'd be left with x squared minus 4x plus 4. And that means because the x squared minus 4x plus 4 is going to factor into x minus 2 times another copy of x minus 2. So I'm going to have an x, and then I'm going to have a copy of x minus 2 and another copy of x minus 2. Since there's only one copy of x, I'm going to have one fraction involving the x, a over x. Then I have at least a copy of x minus 2. So I'm going to go b over x minus 2. And since I have another copy of x minus 2, my third fraction is going to be c over x minus 2 squared. And again, those could have been written in any order. Doesn't matter what order they're written in. But you're going to have three fractions. One with denominator of x, one with denominator of x minus 2, and one with denominator x minus 2 squared. Does that make sense from after we factored anyways? Why that works? So the two repeating factors, I got to do factor squared. And then the one lone factor, we just have to do it by itself. To get a common denominator, you would want to multiply this first fraction, a over x, by x minus 2 times another copy of x minus 2. So x minus 2 squared. Right, you need an x minus 2, and another x minus 2 to get common denominators. So a needs to be multiplied by x minus 2. Second fraction, the b would need to be multiplied by an x and also an additional copy of x minus 2. And then the third fraction, that c, the only thing we actually need to multiply that by is the x, because we already have 2 copies of x minus 2. All of that should add up to the numerator of our original fraction. I'll do this in 2 steps. When you multiply x minus 2 squared, you get that. X squared minus 4x plus 4. X times x is x squared minus 2 times x minus 2x. Let's see. So we have a x squared minus 4ax plus 4a. When I multiply a through. When I multiply b through, I get bx squared minus 2bx. And then cx is just sitting there. And then, as usual, we look at the x squared terms. On the left-hand side, I have a and b as coefficients of x squared. On the right-hand side, I have a 1. So a plus b equals 1. comes from the x squareds. The x's, so we get negative 4a times x, negative 2b times x. And also a plus c times x. All of that is adding up to give you a negative 3. And then lastly, the constant. Well, there's only one constant term on the left-hand side. That's negative, or that's 4a. That's positive 4a. And on the right-hand side, the constant is negative 4. You can either solve this through using a matrix. You can also solve this by saying, well, that means solve this one for A, plug that number in here, solve for B. Once you have A and B, you can plug those two in here, solve for C. It doesn't matter which version you use to solve. I think I'll use the matrix. This is going to be a 3x4 augmented matrix with 1, 1, 0, 1. We phrase that. So I'm going to go R, R, E, F on the augmented matrix 1, 1, 0, 1. So that's my first equation. There's no C, so I put a 0 in the C spot. Negative 4, negative 2, 1, negative 3 is going to be my second row. 4, 0, 0, negative 4 is going to be my third row. And when I solved that, I essentially got A is equal to negative 1, B is equal to 2, C is equal to negative 3. You can double check if you want and see all that works. So I need to integrate negative 1 over x, a plus 2 over x minus 2, and a plus a negative 3 over x minus 2 squared. These first two are going to be fairly straightforward to integrate using natural log. That last one I'm going to rewrite so that I can integrate that using the exponent rule, right? Variable to a power rule. So we have negative 1 times natural log of x plus 2 times the natural log of x minus 2. Normally it'd be minus, let me write the first thing first. X minus 2 is going to get raised to a negative 1 power when I do power plus 1. When I divide by this negative 1, negative 3 divided by negative 1 is going to be a positive 3. And then I would also have to divide by the coefficient of x, but that's 1. That's not going to change anything. And then I have to tack on a plus an arbitrary constant at the end. again, that arbitrary constant at the end is not the same thing as a c. If that confuses you, just use a different letter for this piece. But that's it, that's the whole answer. Again, lots of different ways to rewrite that. But I'll leave it as is for right now. Any questions about this process? No. So if we have repeated factors, then we create this technique where one fraction has denominator of x minus 2, the next fraction has denominator of x minus 2 squared. And if we add another x minus 2 in this, we have x minus 2 to the third power, third denominator. Doing the same thing. All right. So there's one more deal. One more little crappy thing that happens. So let's say we have a denominator of x minus 1 times x squared plus 1. Now, it doesn't have to be just x squared plus 1. This rule is going to work for more general quadratics that are like x squared plus 1. All right. Wait, know how to factor x squared plus 1? If it were x squared minus 1, it'd be x plus 1 times x minus 1, right? Difference of squares. But this is the sum of squares. And that means that this is not this x squared plus 1 part. You can't factor over the real numbers. You'd have to use complex numbers if you wanted to factor. Okay. So this one doesn't factor over the real numbers. Now, one of the nice things about polynomials is that when you start factoring polynomials, if it's a polynomial to a third power, then it'll always factor into a linear piece times a quadratic piece. Okay. If it's a polynomial to the second power, so it's a quadratic, sometimes it factors into two linear pieces, and sometimes it doesn't. This is the case where it doesn't. By the way, if you had a fourth degree polynomial, you could always factor it into quadratic times quadratic over the real numbers. You guys know that? So the only time where we don't factor over the real numbers is the quadratic scenario. Okay, so it'll break down into pieces, but sometimes our quadratics don't factor over the real numbers. And then we are out of luck in terms of the techniques that we've just seen. Right? So what we do is we create a new technique. The x minus 1, well, that's just going to be an a over x minus 1. The x squared plus 1, since it's quadratic, what we have to do is we have to create a linear piece in the numerator. And then we go through this process of figuring out the A, the B, the C. Now, when we go through this process to get a common denominator, the A is going to have to be multiplied by x squared plus 1. But be very careful when you multiply that right-hand fraction. On top and bottom, you're going to have to multiply by x minus 1. But when you multiply on top by x minus 1, make sure that distributes. And you have to multiply the entire numerator by x minus 1, not just one of the pieces. So we can multiply this out. You get a x squared plus a plus bx squared minus bx plus cx minus c equals x plus 3. Okay, multiplying that through. So just distributive property. The x squared terms on the left are a, b. So we get a plus b. On the right, we have no x squared terms. So a plus b have to add to give you 0. The x terms on the left, you have a minus bx and a plus cx. On the right, you have 1x. And then the constants on the left, we have a and a minus c. And on the right, we have 3. I'll do this by hand. Is that all right? Here's a quick way to do this. If you add up all 3 equations, what's going to happen? You'll get 2 a's, the b's will cancel out, the c's will cancel out, and you'll get 2a equals 4. See that? Add up all 3 equations. 2a equals 4, so a has to be 2. A and b have to add to 0, so that means b has to be the opposite of a. So b has to be -2. If a is 2, then minus c has to be 3, so c has to be -1. A and B have to be opposites based on that equation. Since A is 2, B is -2. And then if you apply it to this equation, you'll see that C has to be -1. Or if you apply A equals 2 to this equation, you'll see C has to be -1. Plug those in. And so we get another integration, which is 2 over x minus 1 plus -2x minus 1 over that quadratic that can't be factored. This piece is pretty easy to integrate. This piece is more difficult. All right. That piece, if you want to integrate it, is going to be more difficult. In fact, this piece is easier to integrate using breaking that up into -2x over x squared plus 1, and then -1 over x squared plus 1. That makes sense. And then the -2x over x squared plus 1, in fact, integrates fairly nicely with the u substitution. So -1 over x squared plus 1, you actually have to go back to your trig substitution, and you get, I want to say arctan or arcsecant, I forget which one. Kind of messy, but. All right. So I'll just state this. This is an easy thing to integrate. This is more involved. Which is the original reason why we wanted everything to look like this anyways, right? Again, it's doable through substitution and trig substitution, all right? But I'm not gonna spend 10 minutes on doing something we've done in other sections, right? We don't need to spend lots and lots of time on that. And it is doable through substitution and trig substitution. Break it up a bit. But for right now, we'll just leave it as is. You see the technique, right? So the technique is this one. So anytime we have a quadratic that's not factorable over the real numbers, we run into that issue. Okay? We run into that issue, and that's how we have to do it. And then it becomes much, much more difficult. By the way, what if we have a quadratic that's not factorable with another quadratic that's not factorable? These next couple, I'm just gonna say, how would you set this up? What would the fractions look like? I won't do the factoring part. I won't get the A, the B, the C. Does that make sense? I'll just set it up. So in this one, we have a quadratic in the denominator that is not factorable over the real numbers times its match, which is again not factorable over the real numbers. And so how would we break this up? Anybody have any guesses? Well, in the last one, when we had a quadratic that wasn't factorable, we had to use a linear piece on the top, right? So probably have that again. A linear piece on the top. What should we do for the second denominator?
X plus D,
Say that again.
did you see X plus B?
Yeah, so in the numerator, you'd use again another linear piece. And in the denominator, you do that thing squared because we have two copies of it. Again, I'm not saying that that's gonna be, that would be a very hard thing to integrate. And now we have 4 unknowns to find. So that's why we're just setting it up, right? We're gonna say it is doable, but it's a lot messier. Okay. Does that work? So that would be the setup. Let's do one other. I want you to on your notes or whatever, just do the setup for this one. Don't find the A, B, C, whatever, how many things require. We have x plus 3 times x minus 4 squared times x squared plus 18. That x squared plus 18 is not factorable over the real numbers. I'll just tell you that. By the way, x squared plus a number is not the only thing that's not factorable over the real numbers. There are some other quadratics that are x squared plus 2x plus 5. For instance, would not be factorable over the real numbers. It don't just have to be that form, but that's an easy form to recognize, x squared plus a number, plus a positive. Oh, it's not factorable over the real numbers. All right. So when we integrate, when we break this up, you have one copy of x plus 3. Again, the order doesn't matter, but I'll just go in the same order we're going in here. We have 2 copies of x minus 4. That means, since x minus 4 is a linear piece, I'm gonna do b over x minus 4. And then a c over x minus 4 squared. And then I have this piece that is a quadratic that's not factorable over the real numbers. So I put my dx plus e, a linear numerator, over that single copy of x squared plus 18. And that would be my setup. So if we ever have combinations of these rules, then the setups look like the combinations you'd expect. Any questions about the breakdowns here? That straightforward? How the setups go? Again, as you can see, I'm not gonna ask you to integrate a really messy, ugly looking, something like this. This would take a really, really long time to do. It's, I should say a really long time. It's not that long if you're willing to, you know, program a computer to do it. Because finding the A, B, C, D, and E by hand takes a long, long time. But, again, if you have a computer program, that's what they excel at. Doing things very, very quickly and through some brute force calculations. So there. But I won't ask you to do something like that on the test or the homework. Setting it up, yes, but not going through and finding the A, B, C, D, and E. That'd be a long way. Okay. All right, any questions about partial fractions, those breakups? Again, repeated factors, we've dealt with 2 unique factors, 3 unique factors, 2 factors that are the same, 2 factors that are same, 1 factor that's unique and 2 that are the same, right? Lots of different combinations of those. Quadratics that you can't factor over the real numbers. And then some messier setups. Okay. So that's the idea of partial fractions. Now we have about 9 minutes left. I think what I'm gonna do right now is I'm just gonna leave 6-7 and 6-8 all for next class period. Okay, those are both gonna be covered in one class period. It's about integrating out to infinity or integrating close to an asymptote. All right, so when we do a definite integral and we're by an asymptote, or one of our bounds is an asymptote, or one of our bounds is infinity, what are we gonna do with that kind of thing? All right, so we'll see those things next time. You'll also notice that there's no 6-6 homework. We're not gonna cover section 6-6 in this class. If you wanna look that up, you can. Yep, there's the website. So you can click on the website, look it up, view it online, whatever you want to do. All right.
You said on the exam we're allowed to use notes and a calculator?
Yes. Yep. You can use notes and a calculator on the exam.